All right, so welcome back to the class, and so we're currently going to have the final lecture for so May 4, and after that we're gonna have a final exam review of May 6, and again that I will be giving additional final exam review on May 11, and that's pretty much it. And then next Wednesday that's gonna be the final exam. And I know most of you actually have the second final exam solutions, and this is the thing that we going to look at that. Where did I put the final exam study guide? So this is the thing that we going to look at the final exam review solution, and there were around like 28 questions, and each question has different parts. So I do not really completely simplifying all of these answers for that part, but you can check. This is pretty much the thing that we need to do. And for each question that I actually write down whether the integral is improper or proper integral, so you can double check that part. And so when it's become improper and when that is a proper integral. So we need to make sure that we understand this, okay? Also the limit part that we very likely to use the Hospital rules, but you might have a certain problem that with that Hospital rules for that part. So making sure if we have a certain problem like this, that we can solve for that completely, okay? So I'll be going over all of these questions, and also I will help people set up the integrations to find the volumes or the area. Okay, the area was pretty straightforward. That we're going to take the upper, subtract the lower area, and then we'll take the integration for that part between two functions f and g. But for the volume that we need to know where we're going to use the washer method or the shell method. So I check two ways. We can do it both ways using v equal to pi r squared, or v equal to 2 pi h x. So those are the thing that we need to understand. And again, that is whether we're using the shell and when we're going to use the washer method. Okay, so those are two complete different methods that we take into account. And the next part was the areas, and then we need to know how to verify the solution to differential equation. So maybe one or two questions on the exam, and that we differentiate it. Usually that you have to differentiate twice, and then we compare it to the original functions. And actually gave this quiz on the quiz number 5, I believe, right? And also if whether or not it is not a solution and why, you need to prove them. You can't just say it, this is not a solution. You have to write them down, y primes or y second prime for that part. And of course that we have a certain part on the chapter 6.1, correct? So the 6.1 is literally the part that we can see coming from acceleration to initial positions. I'm sorry, acceleration to velocity and to position to all of that. Basically concerns about the integral or derivative. So we need to take care of that. And very likely if the question asking us to do the to find a position as a function of time, then we need to take the equation without a and b, right? Without a boundary. If the question is asking us to deal with the distance, then we need to take the absolute value of at either velocity or whatever acceleration from A to B. So those are two different stories for that part. And then we also have to do with chapter 7, where we did not spend a lot of time working on this exponential function, but we did spend a huge, maybe 1 or 2 lectures, 1.5 lecture for that part. And then we deal with that using y equal to y0 or kt. So again, that this is going to be the part that we need to solve for the constant, and sometimes we need to solve for the population for that part. The constant k doesn't necessarily have to be the whole number, right? It can be just the ln of 1.2. I divide both sides by 50,000, and then divide both sides by 10 after we take the ln. And sometimes we need to find these particular solutions of a differential equation. So let's say I give you a certain function like that, and then we need to deal with the the first derivative and the second derivative by integrating. Finally, that we have a certain problem such that we have to consider whether that series diverges or converges. So how many tests do we have? We have 10 different tests. Whatever the tests that we use, need to write them down. I grade most of your quizzes, and I feel like you guys did not write them down. A lot of parts. So again, when the questions involve factorial exponential, then we use ratio test. And when we're going to use the integral test definitely be a question like that on the exam. And on a quiz that I actually saw people use integral test for that part instead of the telescoping test. If we know that this is the telescoping series, that we can simplify them, but I don't see a lot of people do so. Yeah. So also when we see the k power, when it raised to the power k, then we need to apply the root test. And usually the root test and ratio tests are really, really important for that part. And whenever we have the alternating series, that we need to make sure that the functions is decreasing, right? And the limit go to 0. It'd be only, I actually give that questions on the quiz, and very few of you who actually determine if the function is a decreasing function, not a, it's not a, I mean, decreasing meaning non-increasing function. So, and then if it doesn't satisfy the first condition, then we don't have to take the limit for that, even if the limit goes to 0. But this is not the series that approaching. Question number 23, the telescoping series that we can factor it out and rewrite them in terms of the thing that we have. And Maclaurin series for f(x) that we can use the Maclaurin series. Basically, the Maclaurin is the special case of a Taylor series that's x equal to 0. And this is a very important part, the Maclaurin, that we can solve for that. There is actually another way that we can do so, because we know e to the x will be x to the k over k factorial that we learned from Thursday, and then I multiply by x, that will be x to the k plus 1 over k factorial. But since the questions asked us to do the 4 terms for, actually I did 3, so I apologize for that. No, 4. So 1, so add up 0, 0, yeah, 1, 2, 3, 4, yeah. Yeah, I did 4. And so today we're gonna work on the rest of the questions. We want to find the radius and interval of the convergence. And also that we going to use that condition to solve for another series, Taylor series representation of g of x. So what's going on for that part is, again, that I did not post a lot of video for that part, but definitely gonna be a videos on another videos on chapter 11, and that's gonna be so again today gonna be the last day of the lecture, and after that we're gonna have the final exam review on May 6th and May 11th, and that's pretty much the day that we will take care of that. Yeah.
Do we have to be on Zoom next Wednesday for the test?
I don't think so. So because if I can't stay for 5 hours,
Okay.
a certain time for that part. So yeah, like last time, but this time you're gonna be really careful. There will be some question that testing you. I noticed that you guys use some of you guys use different methods to solve a problem that I never taught. Yeah, so if you consider that and actually people doing exactly the same way, so you gotta be really careful in the final exam. So this is all I can tell you. And so just to do your best and whatever that you
so
have.
you only.
I'm sorry?
Are you saying that it's only okay to use methods that you've taught?
That I taught usually, but I don't
What
want
if
you
we
to
saw something in a YouTube video and we're not sure if, and we can't remember if we learned it from a YouTube video or if we learned it from you?
Yeah, so I agree. So most of you also know the fact that I post some useful videos for self-study. If you watch the last 2 videos from organic chemistry, and then you can definitely see how they expand the Taylor series and the geometric and some kind of series that we have. But what I'm saying is that if the people who use, I mean, if one person using different method, that's fine. But if all of you using different method to solve that problem, so I'm going to put the question mark on it, right? But usually I don't. I understand this is a very difficult time to learn, and many of you who learn it from outside resources, that's perfectly all right. But what I'm saying is that if one person using different method, 2 is good. But all of you using different method, I will be like, you see what I'm saying, correct? So I'll be wondering what's going on. But usually, most of you did the second exams pretty well, but it's except for some, and I mean pretty well, meaning that the average should be around 75. So that I would say that's pretty good for the second exam. So the final exam, I do expect people to spend time working on a certain videos and a certain homework problems, and especially the final exam review. I actually noticed that there was some typo from last time that I put on the answers for the final exam review, but I fixed them. So make sure that you download the news updated version, so that we can see what's going on for. Now we're gonna continue on the final exam. So again, today gonna be the last day of class.
Wait, Professor?
Yeah.
I just had a question on
Yeah.
the last. So on top of because I also use like YouTube, like Organic Chemistry Tutor or Khan Academy video.
Yeah.
But there's also something like Calc Workshop. That like is it like, because obviously there's not everything is going to be covered.
That is true. That is true. So I actually cover most of the part, but yeah. But when you use
yeah. So like, but is it like if we use like a method from one of those like online like
that is fine. That is fine. That is perfectly acceptable. But just give me a link of the method that you learned, and I fully accept that. So it is perfectly okay. Yeah. Okay. So let's say what I use that method from that tutor, posted the link 9 years ago, and some people actually learned the put name, which is the math competition test for all the undergraduate school. At most, reward was granted by the Harvard or MIT students. So they actually post a link and then it's the taught how to solve a problem, you know, that's perfectly good for me. So I don't mind if you guys just do so. Is this going to be it's pretty much the I might consider giving people the PDF file for that part. So I feel like that's gonna be fair, because or maybe I just write down the questions and type it on Blackboard, but it's definitely not gonna be the incident that we have on the second exam where there's no question being asked. And so and then and again that a final exam um, will be typed up. Maybe it's just a PDF file. It's easy for me. Just do the PDF file, and then everything should be all working. Would work for that. It's just like the question that we have the final exam review. So I mean, it still took me a while to work on a Word file, but it's perfectly alright when you post solution for that. But there's no solution posted on the final exam. When you take it, then you I mean, you can't just ask me about, hey, what is the final solution? I can give you any solution that we have on the quizzes, exams, classwork, whatever it is. But on the final exam, that I do not write down a solution because of the fact that we might use this for the future semester. So once you take it, then you gotta leave it for that part. So, and again, that the where are we up to right now? So now we're gonna go to the last, pretty much the last part. And why this is going to be the last part, because again, that 11.2 will be the main, also a very, very main course that we're going to have right here. So what are we working so far? That we have worked through the Taylor series, and then Maclaurin series. We know how to expand it using derivative, right? We know how to take care of that. And this is actually a chart where we fight down all of these Taylor series at x equal to 0. We have a Shing, we have a Koch, all of those that we skip, so you don't have to worry about that. We also have the binomial, but we don't really touch that. We don't really touch these things very often. So we have the ln of 1 plus x, sine, cosine, e to the x, and all of this function will be written down relatively easy for us. And then I will show you how to do so. So the first part that we need to understand was we know the fact that the from a geometric series that we have x to the n. Oops. So this is not really important, but I still need to put them down. 1 minus x to the n over 1 minus x. So this is the geometric series that we can see. So this is the answer will be 1 plus x plus x squared and plus dot 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 up to xn, right? And then we can rewrite the answers from 0 to n, x to the n, x to the k, as simple as we have right there, right? So this is what we have for the series. So we set up, so x, let's say x is very small, and then the series is going to converge, right? So why it is so important for x less than 1? If x greater than 1, the top going to be exploding relatively quickly for that part. So it must satisfy the convergence. So this is what we call the radius of convergence for the series. So this is what we call the radius of convergence, right? So you see how important that is if we don't have this. Okay? So what's going on for that part? And meaning that we don't know if the series actually converges or diverges, but the series, we know the fact that it's going to converge when the x less than 1. Why it is so important? Let's say we take 0.9 and then you rate to the 1,000 power. So you know what's going on for that part. So let's say we take x equal to 0.9, and then I want to figure out the x to the n, x to the 1,000. So we're gonna take 0.9, you rate to the 1,000 power, and I believe if you do so on a calculator, you're gonna get 0 for sure. And so that would be the thing that we're gonna utilize on the series. Even if you take 0.99 or whatever the value is, so it's also give us equal to 0 for that. So, and we're gonna have the, let me just show you on a calculator and see how it looks like before we start the questions. So let me just take like 0.99 and then I rate to the 1,000 power. So I almost got 0, right? So the number really very, very small. When we have like n, it becomes really, really big. So whenever it's less than 1, so this term goes to 0. So when the term goes to 0, then we have the convergence series, so that'd be 1 over 1 minus x. I can be written that. So this is converges for any value of the x that we have. I'm sorry, for x less than 1, and then we're gonna get, we can rewrite the answer, which is 1 plus x squared plus dot dot dot, go to x to the n, and it can keep going forever because the infinite series, you go from 0 to infinity, x to the k. So this can only be satisfied when we have the radius for x less than 1. In other words, we can rewrite this in terms of negative x, less than x, and less than 1. Okay, so when x equal to negative 1, and we know the fact what can we tell about the series, and when the x equal to 1, what can we tell about the series? And again, the x cannot be 1. If x equal to 1, then we have undefined at the bottom part. And a very important thing that we should learn, how can we using that series? We learned it from last time, and how can we solve for the series expansion for 1 over 1 plus x, right? So again, that what we need to do was we noticed that 1 over 1 minus x would be this, and how can we solve for the series 1 over 1 plus x? So I just need to rewrite this in terms of 1 over 1 minus x. Why do we have to rewrite them? Because we need to keep the negative side and for this part, and then we can also deal with that. And then can we write the series? So this is a very important trick that the reason why we call this is a trick, and I'm going to replace x by negative x, as simple as that. X by negative x. Okay, so remember, this is what now we call this is the x, right? The whole terms right here will be similar to that, 1 over 1 minus x. So I replace all the entire infinite series by 1 minus x and plus, so this is x squared, I replaced by negative x squared, negative x squared, that's still be positive, and then plus negative x to the 3, and plus negative x to the 4. I'm sorry, what am I writing right here? So I apologize for that. So this is negative x to the 3 and negative x to the 4, and so on and so forth. And then it's go to infinity, right? And then I can write the terms as 1 minus x and plus x squared and minus x to the 3rd plus x to the 4, and so on and so forth. And then minus x to the 5th plus x to the 6th and so on and so forth. And then we can check that part. It can rewrite this geometric series with respect to from 0 to infinity. And so because we have a negative term, so I'm going to put down -1, right? So, and then when k equal to 0, it's going to be 1. When k equal to 1, it's going to be negative. So that'd be -1 to the k and x to the k as well. And so this is what we call the infinite series for 1/1 plus x. And we can also check this is the thing that we have right there. And we need to include the series where my x less than 1. And that is a very important, very important part. Okay, so we need to have the radius for that still be the same, which is x less than 1. Okay, so it's really important to keep the radius of the convergence, because if we don't keep them, we don't know whether or not the series is going to converge or going to diverge. The same thing for this part. So let's say, how can we look for the ln of 1 plus x, right? But the fact is, by the radius of the convergence, x should be between 1 and -1 from the previous example that we have right there. So I can also write without the parentheses, because I know the fact that the x less than 1, so the sum have to be positive. So I can rewrite this without the absolute values. So we know the fact that this, when I take the derivative of 1 over 1 plus x, and we know the fact that it's gonna be the ln of 1 plus x. So what we can do in this case is I'm going to integrate the polynomial series, and that's how we're gonna get the ln of 1 plus x. So I just literally need to integrate every single term for that, because this is a sum, right? So all of this is a sum. So when I take the integration, meaning that we just take the integrate of 1 minus x plus x squared minus x to the third plus x to the 4, right? So in other words, all I need to write them down was that I can write down the ln of 1 plus x by integrating the entire function, which is 1 minus x plus x squared and plus minus x to the third, and so on and so forth. I just integrate them with respect to dx, right? Because we know the fact that 1 over 1 plus x, which is those terms. And in other words, I can solve for this series using this method. So, so the fact is that we going to integrate all of this with respect to x, and then when I integrate that, I'm gonna get, so one integration will be x, right? And then x integrations, that will be negative x squared over 2, right? And then x to square integrate, they're gonna be x to the third over 3. And x to the third, when I integrate them, so I'm gonna get minus x to the 4 over 4. And then we're gonna plus x to the 5th over 5 and minus x to the 6th over 6, and so on and so forth. I can rewrite the entire term with respect to, so that would be -1 to the k as well, right? And then we know the fact that the x will be going from 1, right, from k equals 0, still be from k equals 0 for sure, and go to infinity. And this is how we're going to write them down. So that would be k plus 1 over k. Okay. And this is the thing that we need to put down on this part, over k plus 1, I'm sorry. And this is the thing that we need to write them down. So in other words, we can have the ln of 1 plus x, which is -1 k plus 1. I mean, it started from 1, so generally you can start from 0. It's going to be the same thing as we have right there. And what the question, what the thing that we have, what the lecture that we have is, we just need to move the index, right, from k equals 0 to k to 1, and then we're going to get the same things that we have right here. Okay. So moving the index also a very important technicality. And for that part, in other words, I can also solve for ln of 1 plus x. So instead of writing down the entire functions, so we know the fact that this will be the integrations of 1 over 1 plus x and dx. And so instead of just working on the entire sum of the polynomial, so I can work on the term like that. So just rewrite integrations of -1 raised to the k and times x to the k. So this is what we need to figure out. And the integrations of that part start from 0 to k to infinity. And so I just need to take the antiderivative for -1 to the k. So -1 to the k is just -5, and we just keep it like that. We don't take the antiderivative for that part. Okay, and then after that we need to take the derivative of x to the k. That we know the fact that derivative for x, I'm sorry, the antiderivative for x to the k will be x to the k plus 1 over x to the k. So this is the thing that we need to put them down on that example, right? And then so I can just rewrite this in terms of x to the k plus 1 over x to the k. I'm sorry, over k plus 1. And so we need to make sure that this the radius of the convergence will be x less than 1. Okay, so we need to make sure that the radius have to be between 1 and -1. If it's go beyond that, it doesn't work that way. And so and then it's start from 0 to -infinity. Then the series is going to converge this. Okay, so now we have another function. So we need to write down the psi. So the psi of x would be x minus x to the third raised over 3 factorial. So let's say we have the size of x. Using a Taylor series, we're not going to do it. We learned it from Thursday. I can do it again if you want. Well, Taylor series, the center is 0, which is Maclaurin. And we're going to get this is x minus x to the third over 3 factorial. All right, because the second one is 0 plus x to the 5th over 5 factorial. And then we're going to have to take minus x to the 7 over 7 factorial. Right, and then so the first 4 term, we write one more term that doesn't cost us anything. So that would be x to the 9 over 9 factorial. So you see the fact that all of these terms are going to 3, 5, 7, 9. So this is 1, this is 3, this is x to the 1 over 1 factorial, and so on and so forth. So I can rewrite the sum with respect to -1, right? And -1 to the k, correct? Because the first term is positive, second term is negative, positive, negative, positive, negative. And I can just go to from x to the, so 3, 5, 7, 9. So that would be 2k, right? And plus 1 over so does the bottom also be the same? So that'll be 2k plus 1 factorial. Okay. And okay, let me just cost amount. And this is from 0 to infinity. And what is the read-ups of conversions? So x can be any number. So we can just rewrite them. X would be less than infinity. Okay. So what's going on for this part is that I need to solve for the cosine, for example. Right? Find the series for cosine. The series for cosine x. Okay, so using the size of x function, for example, this is also the final exam review. And how can we solve for that? So the fact is that we're going to deal with them using derivative, right? So we know the fact that or we can take the antiderivative, but we're gonna get negative cosine, right? So we know the fact that the size of x, when I take derivative, so we're gonna get the cosine of x. So this is the fact that we should know. And if you don't know what it is, you're pretty much going to having a lot of trouble in the final exam. So instead of that, I just differentiate every single term, because remember, those are just the sum of the polynomial functions, right? So I can just rewrite any function with respect to the sum of the polynomial functions, and using the Taylor series expansions. And what we need to do was that when you differentiate it, we're going to, so the size of x, so the cosine of x, when I define, will be the size of x derivative, right? And when I differentiate the size of x, I get cosine of x. So meaning that we're going to differentiate x minus x to the third over 3. I mean, this is one way to get it, but if on a final exam, if the questions ask us to find the cosine of x, and we literally need to use the same method that we have. Okay, so x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial. Right, so we need to take the derivative for all of this. X to the 9 over 9 factorial. So I need to take derivative for this, right? So when I take derivative for that, so remember when you take the x to the third over 3 factorial, when I take derivative for that part, I'm gonna get 3x squared over 3 factorial. So, and then 3 factorial over 3. So we're gonna get 2 factorial over 2 factorial. Right. So the entire term that we're going to have is 1 minus x squared over 2 factorial. Right. So all of that is going to be the term that we deal with that, and then we're gonna add x to the 5. So over 5 factorial, that'll be x to the 4 over 4 factorial. Right? So 5x to the 5 over 5 factorial will be x to the 4 over 4 factorial. And then we do the same thing for 7. You pulled out a 7. So that'll be 7x to the 6 over 7 factorial. That we're going to have x to the 6 over 6 factorial for that part. And finally, that we're gonna, so we keep going, whatever. So that'll be x to the 8 over 8 factorial. So I can also rewrite this series with respect to dot, dot, dot. Just keep going forever. And I can also rewrite this series with respect to the sum from 0 to k, 0 to infinity. I'm sorry about that. Right? And then let's go from, so we have a negative term for the second right? 4 is same thing, so that'd be -1 to the k. And then we rate to the power x to the 2k instead of 2k plus 1 over 2k factorial. Okay, so this is the thing that we have right there, over 2k factorial. Right, and then 2, 4, 6a, so that'll be 2 for k equal to 1, 2, 3, 4, 5, and so on and so forth. In fact, I can also so I can also rewrite the size of x derivative. So meaning that I'm going to take, so we know the fact that the size of x will be the -1 to the k, rate to the x to the 2k plus 1 over 2k plus 1 factorial. So we know that from the very beginning, this is from 0 to infinity, right? And then I just need to differentiate this, the entire term, right, coming from here. So this is the thing that we have, right? I just need to take derivative for that part. So when I take derivative, I'm going to bring down 2k plus 1. So this is from 0 to infinity, right? And then we're going to have -1 to the k, and I bring down 2k plus 1. And then we multiply by x to the 2k, because of the fact that we can also bring, so we subtract the power by 1, right? And then we bring down the terms, and the bottom will be 2k plus 1 factorial, right? So remember that 2k plus 1 factorial, again, it's going to be the same thing. If we have 3 over 3 factorial, we're going to get 2 factorial. So 2k plus 1 over 2k plus 1 factorial, that we're going to get 2k factorial on the bottom. So we can just check the answers. So 2k plus 1 over 2k plus 1 factorial. Again, that we can rewrite 2k plus 1 factorial will be 2k plus 1 times 2k times 2k minus 1, and so on and so forth, meaning that this will basically 1 over 2k factorial. And that's pretty much the thing that we have right there. And so we can also rewrite the terms with respect to from 0 to infinity and -1 to the k. Again, I'm not going to take like every individual's term into account. I just use the term that we have for psi, and then let's take the derivative for that part. Times x to the 2k and over 2k factorial. So again, by doing so, it's going to save you a lot of time instead of just writing down every single term and then rewrite a formula for that part. So this is the check, and this is also be the check. So we can use a sign to figure out a cosine, for example. So the same thing. And how can we use, how can we figure out a cosine of x squared, right? So for the entire x squared, not only for the x. So we know the fact that the so how can we find the series for cosine of x squared? But we know the fact that the cosine of x, as we have from the lectures earlier, so we can also have this done. Let me just check the access real quick. Yeah, can I go back for a second? The answer is absolutely yes. So I do two ways. So the first, I rewrite the Taylor series expansion from the size of x. I take derivative for every single term, and then they got the same thing as -1 to the k and times x to the 2k over 2k factorial. I can simplify that like that, but I feel like doing that, it was basically too slow. So what I did was I used the entire Taylor series expansion for size of x. I differentiate the entire term. So I bring down 2k plus 1 over 2k plus 1, we know the fact that this is going to be like 2k factorial. And also the term that we bring down a power, so that the power should be lowered by 1. Instead of 2x to the 2k plus 1, you're going to get x to the 2k. And we see that the power actually going down by 1 for every term right here. And we have the same thing. And then also the, you know, the thing that we have right here also be the same. So let's say I want to write down the power series of cosines of x squared. So I can use the cosines of x and then I figure out a cosines of x squared. So we know the fact that use the cosines of x, so we can have this is from 0 to infinity and -1 to the k times times x to the 2k and divided by 2k factorial. Okay, so divided by 2k factorial for that part. Let me just rewrite the term. Okay, so using this, again, that we can also, so I replace, so we need to replace, we replace x by x squared, right? Why do we have to do that? Because we need to use the cosines of x to solve for cosines of x squared, for example. And remember that the power series in this case is x go to infinity. X can be any values. So the radius of conversion, I will let you know what it is. And after that, so it's, remember that for sine, cosine, we have no application for x. But for some term that we have to make sure that x less than 1 for the radius of convergence. So for the sines and cosine, this is what we need to do. And I've replaced x by x squared, meaning that I'm going to replace this x by x squared. So I can also have the cosines of x squared will be equal to the sum from 0 to infinity, -1 to the k. Remember, I've replaced x by x squared, so that becomes x squared, and rate to the 2k, right, over 2k factorial. But remember that we just replace x by x squared, simple as that. And we can have the series that go from 0 to infinity. And this guy will be from -1 to the k. X to the, so x to the 2 times 2, 2 and the power and another power that we need to multiply the power together. So that becomes x to the 4k over 2k factorial, right? And so we have no obligation for that part. So we want to know if the series converge or diverge, for example, we can take the ratio test, and then we know the fact that the cosine, remember the cosine of x is bounded between 1 and -1, right? So I'm pretty sure that most of this series for sine, cosine, basically, the sum should be less than 1, right? So it should be converges, as simple as we have right there. So now what we have was, so let's say we're going to test if the series converges or diverges. I claim that it's converged for all x, regardless, okay? How do we know that? We're going to check it later on. So we're going to go back to all of these lectures and we check them out. But now we're going to go to the series 1 plus 1 minus x. I just rewrite them. So that would be equal to the sum of x to the k, right? Where k is going from 0 to infinity. In other words, I can going from 1 plus x squared plus x to the 3rd, and so on and so forth. And then we keep going until we finish that. so and so on and so forth. But we need to make sure that the radius convergence will be x less than 1. So we're going to testify all of this using the ratio test, or in fact that we can also use the root test for this example. So that's going to be a lot easier. So so what's going on for that part was we're going to write 1 over 1 plus x that we learned it. And so let's say we use the 1 plus x squared, okay? So meaning that I'm going to rewrite this terms as 1 over, so I'm going to change to this similar to that form. So we need to keep the negative side first, right? Because I need to have the negative term. And then I can also rewrite this as negative x squared, right? So remember 1 minus x squared and would be equal to 1 over 1 plus x squared. But what we're going to be doing is that we're going to replace x by negative x squared so that we can also rewrite this, right? So I'm going to replace using this guy. I replace that part, and so negative x squared. So remember when you replace negative x squared, we have a negative 1 in front, right? So meaning that we have to keep the negative 1. And raised to the k power is, it might have some negative, positive alternating series from 0 to infinity as well, right? For example. And then I replace x by negative x squared. So we get rid of the negative term. I change that to negative 1 to the k powers, right? And then we also have negative 2k. Okay, so that's pretty much this. So if you sort of feel like, well, I don't understand what it is, you can go one more step forward for that part. I just replace x by negative x squared. So this one will be negative x squared raised to the k. But we know the k will be positive and negative, so we cannot cancel out the negative sign in the front. So meaning that we going to rewrite the terms with respect to negative 1 to the k over x to the 2k. And also x, the rate of conversion should be less than 1, making sure that it's less than 1 for that part. So I can also write the arctangent. I can solve for arctangent of x, right? So we know the fact that when they take the antiderivative for this, I can take the antiderivative for 1 over 1 plus x squared. I'm going to get the arctangent of x, correct? So meaning that I can just integrate the entire things that we just found. So that would be the summations of negative 1 to the k. I mean, you can write out the term. So this term that we have would be, so when k equal to 0, so we're going to get 1. When k equal to 1, so you're going to get minus x squared. When k equal to 2, so that would be plus x to the 4. When k equal to 3, so you're going to get minus x to the 6. So remember that you can write them there in terms of the sums or in terms of the summations. I mean, if you can write them down in terms of the summation, that would be great. But if you can't write them down, you can just write out a sum with 1 minus x squared plus x to the 4 minus x to the 6, and so on and so forth, and then can rewrite them. And so I just need to take the antiderivative for the entire terms right here with respect to x. So what I can do is that I'm going to take the antiderivative. So remember that we're going to keep the summations. We do not change them, right? And after that, we're going to put negative 1 to the k, right? So when I take the antiderivative for 2x, so for x to the 2, x to the k, for example, or x to the 2k, So we know the fact that, so the answer will be x to the 2k plus 1 and over 2k plus 1, right? We just add up the power by 1, and then we divide it by 2k plus 1 at the end. So the thing that we have here, so that become x to the 2k plus 1 and over 2k plus 1. Right? And then after that, we're going to look at the terms, and you can sort of feel like the term can be rewritten. So again, when you take the antiderivative for 1, you're going to get x, right? So we plug in k equals 0. So when k equals 0, we're going to get, so this is done, right? So we can check them out. I can rewrite the terms. So when I plug in k equals 0, I'm going to get x. When I plug in k equal to 1, so I'm going to get x to the third over 3. When I get k equal to 2, so that'll be x to the 5th over, so 2 times 2 is 4 plus 1 is 5, x to the 5th over 5. And again, that we can also find when k equal to 3, so that'd be x to the 7 over 7. So and so on and so forth for that part. And then we can rewrite all of these terms of the terms. Or if we check them, we can take the antiderivative for 1 minus x squared plus x to the 4 minus x to the 6. We're going to get the same thing as x minus x to the third, and so on and so forth. Keep going. So this is how we solve for the arctang as well. So any functions, I can use the previous ones. I can find out the, I mean, there's so many ways I can do so, right? So first, I can use the Taylor series to solve for that. Second, I can use any specific function that I know earlier and solve for that. So in this case, arctang is using the antiderivative of 1 over 1 plus x squared, and then I can deal with that. So that's pretty much things. Now we're gonna, but the most important thing is that how do we know if the term is, how can we know if the terms is convergence, right, or divergence, right? And so this is the thing that we're trying to get at, and the very important that we should know. For example, when we look at the size of x, so we know the fact that the size of x is so size of x. So the term that we have here would be equal to the summations of -1 to the k over times x to the 2k plus 1 and over 2k plus 1 factorial, right? How do we know if the size, what is the radius of the convergence? So from 0 to infinity. What is the radius of the convergence, right? So what is the radius? What is the radius of convergence, right? So what is the value of x that's going to make this series converges? In other words, what is the value of x? The value of x, or the bow of x. What is the bow of x that makes the series converges? Okay, and so this is a thing that we need to need to understand. It's important to know what it is. So what is the value? So we know the fact that there's some certain series that are going to converge, some certain series that are going to diverge, but we know the fact that size of x, the value of psi have to be bounded between 1 and -1. So it should be convergence for all x values. So you can plug in any x, it still be convergence. So this is a fact. So what kind of test are we going to use? So we're going to use the ratio test. Ratio test or root test. Very likely. Why is that? Because most of the power series, right, we use ratio test or root test. I mean, you don't have to use both of them, right? Just need one of them, because right, because of the fact that all of this term in terms of factorials or in terms of the power term. So this is why I always told you guys that the ratio tests and the root test is really, really important. So let's say we don't have to do it twice, right? So approach one, use ratio test. Sometimes we can use root test interchangeably, but you know, either way is going to be fine. So the ratio test that going to tell us that we need to solve for the R. That would be the limit of k go to infinity, right? And then we need to deal with the terms for 8 to the n plus 1. I'm sorry, k plus 1. I'm sorry with that. Usually that they use n plus 1 for n go to infinity, the same thing, but over 8 to the k, right? And then we need to make sure that r less than 1. So this is what we need to deal with, okay? So now we're going to check that part. So how can we check this? And we're going to rewrite. So when 8, so we're going to rewrite the limit of k go to infinity. So remember, when we take the absolute value, that we don't really care about the -1 right to the k, right? So we ignore that. And so I'm going to rewrite the term, so x to the 2k plus 1, so that'll be x to the 2k plus 1 will be k plus 1, right? I just replaced k by k plus 1. Excuse me. So I just replaced k by k plus 1 and plus 1, right? And using the ratio test for that. So, and then the bottom will, I replaced 2k plus 1 by 2. I think I had to open the big parentheses, so that'd be 2. I'm sorry. So 2 of k plus 1. If we know the bottom is 2k plus 3, that's easy, but I need to write them down with respect to 2 times k plus 1 and plus 1. And then in terms of factorial, so when we divide it by ak, meaning that we multiply by the reciprocal. So the reciprocal for x to the 2k plus 1 over 2k plus 1 factorial will be, so we're going to rewrite the 2k plus 1 factorial over x to the 2k plus 1. Same thing. It just flipped the entire fractions of the term series for that part. And then I can simplify that part. So before we can simplify it, I need to solve for this part. So that'll be the limit. I just rewrite them. K go to infinity. And so for that part, we're going to have to deal with x to the 2k plus 1 plus 1. So that'll be x to the 2k plus 3. Right? So the top and the bottom becomes, for the an plus 1 becomes x to the 2k plus 3 over 2k plus 3 factorial. Okay. So what we need to do next for this part is we need to multiply by the same thing. So that would be 2k plus 1 factorial over the bottom is 2k plus 1, x is 2k plus 1. Okay. So remember that x is 2k plus 3 over 2k plus 1, we're going to get the x squared. So x squared, we're going to pull the term out. A very important thing that we're going to pull the term out. So that'd be x to the k go to infinity. We're going to have the x squared term. So I pull it out. Okay, so x squared. So I can actually put the x squared in front of the limit so that we don't really have to worry about that. So the only thing that matter about the limit term will be the k, right? So the x is literally the constants. Generally, you can use any x. It doesn't matter for this part. And then we take the limit of k go to infinity. So now we observe that the fact that, so 2k plus 3 factorial, and then the top is 2k plus 1 factorial. So, so the difference between these two terms will be the 2, right? And then I can also rewrite this, so without the absolute value, so that the bottom will be 2k plus 3. I can rewrite 2k plus 3 factorial will be 2k plus 3 times 2k plus 2 times 2k plus 1 factorial, so they cancel it out on the top and the bottom. So the whole thing becomes this. Okay, so, and finally, so when k go to infinity, this guy go to 0, the limit, right? So the entire limit go to 0. Okay, so the ratio test in this case is literally a little more complicated. Okay, so we're gonna use the root test later on, but generally now this is all we need to write. Okay, so very likely that the series converge for OX. The series converges for OX. Okay, so you can give me any value of x. The term is 0. Multiply by x squared, that's still be equal to 0. So we can just rewrite them. The radius of the convergence will be x go to, it can be any value for that part, go to infinity. I use ratio tests very often, but it's very likely that we can use the root test for that part. That's perfectly all right. So there were certain examples that we can solve for that. So what is the radius and the interval of conversion for the following series, so that we can deal with it. So we know the fact that this guy will be e to the x, right? So how do you know if the radius of the convergence of that? So e to the x is converges for OX, right? So it's gonna be converges for OX in this case. We're gonna check that part using the ratios test. It's really important. So what I need to deal with was I'm going to rewrite the test with respect to x to the k over k factorial, right? And then the k will be going from 0 to infinity. So I want to testify the convergence in this case, right? And then all we need to do was the fact that we take the ratio test, right? We use ratio test. In this case, we get the question involving, we use ratio test involving x to the k and k factorial, because we had the factorial terms. And then what we need to do was we need to take the limits, find the R. Remember, the R converges, remember, on the previous example, the R converges, remember, the ratio test, the R less than 0, it converges, right? Less than 1 converges, the series converges. And this is just something that we learned from chapter 10. When R greater than 1, this diverges, the series diverges. When the R equal to 1, inconclusive, so we need to check the sign. The R equal to 1, the series is inconclusive, so we cannot tell anything like that. So what we need to have on that part was we can try the limits for the series, and the limits go from k infinity. So we will take the x to the k So I'm going to rewrite a term. So that we're gonna take the a to the k plus 1. We take the ratio between the next over the previous terms, and you want to see whether or not this term is going to converges. So I can rewrite the limits for k go to infinity, right? And then I can rewrite the term. So all of this is positive, so I ignore the sign. But sometimes we need to have, because we don't know what the value of x is. So we need to keep that absolute values. So so we're gonna get x to the k plus 1, right? For ak plus 1 over k plus 1 factorial, right? K plus 1 factorial. And multiply by, I mean, we need to divide it by a to the k, but since we divided by the term, so we just multiply by the reciprocal. So that would be k factorial over x to the k. And then now we simplify them. So x to the k plus 1 over x to the k, we're going to have the x right there. So we keep the x. And then k factorial over k plus 1 factorial. And what we need to do for that part is, so remember, k factorial over k plus 1 factorial. This is what we did. We're going to get 1 over k. We don't need the absolute value for that part because k is positive. We don't know if the x is negative or positive, but the k is positive. And so once we deal with that, so we're going to get limit of 1 over k and plus 1. Don't forget that. And so this 1 go to 0 for all x, right? For all x. All right. So meaning that the series converges for all x. The series converges for all x. So the radius of convergence, so x absolute value less than infinity. Or you can rewrite, some people want to rewrite this in terms of negative infinity. This is what we call the interval of the convergence of the x. So this is what we call the interval, right? So this is the radius and this is the interval. So this is how we call interval convergence. So we rewrite the term, the series in terms of a bow between negative infinity to positive infinity. So this is all we can do. So now we're going to take a look at another example for another term, x minus 2 over 4. And so the part A, we're done for the whole problem, for the lecture problem. So we're going to go to part B, that we're going to look at the series where we have the terms negative 1 to the k times x minus 2 k factorial, negative 1 to the k times x minus 2 to the k over 4k factorial. Right? And then the series go from 0 to infinity. How can we find the rate of the convergence without looking at the term? So if everything that go with the k and k, right? So we can apply the root test, or the ratio test is up to you. So in this case, I can also rewrite a term. So we can apply the ratio test, right? So we have two ways of solving this problem. We use ratio test. We can also use the root test. I'm going to show you what it is. Okay. So the ratio test going to tells us that the R will be the limit that k go to infinity of ak plus 1 over ak. And this guy that we're going to take the limit of k go to infinity, and we're going to have a So AK plus 1. So again, that when we take the limit, we absolute value, we ignore negative 1 to the k. So I can rewrite the term will be x minus 2 raised to the k plus 1, right? Over 4 to the k plus 1, right? Remember that. And then we multiply by the reciprocal of the AK, right? The reciprocal of AK, you're going to rewrite this as 4 to the k over x minus 2 to the k. Okay? So, and then, so 4 to the k and 4 to the k plus 1, so we know the fact that they cancel it out, and that becomes 4 in the bottom. And x minus 2 and k plus 1 over x minus 2k, so that becomes x minus 2. So we simplify that part. Remember that k plus 1 over k is become 1, right? So the whole term, that turns out to be x minus 2 over 4. Okay, so how do you know if the series is going to converge? So we're going to go to the limit. So the series converges when all less than 1. So we want so the radius of convergence, we want to find the radius of convergence. So we need to make sure that the r less than 1, correct? So the r that we found will be the limits of x minus 2 over 4. So we need to make sure that x minus 2 over 4 less than 1. And then we solve for that, the absolute value, so multiply both sides by 4. We're going to get x minus 2 factorial less than 4. So now I'm going to break down the absolute values, right? So when we break them down the absolute values, meaning that we need to keep the sign, so that'd be negative 4, go to x minus 2, and on the left side, and then the other one go to the right. And then we add to both sides. When I add to both sides, so this one negative 4 plus 2, so the series that we have will be from, so we add to both sides, and we add 2 for this. And then, I'm sorry, not both sides, like 3 sides of that. So we're gonna, the series converges, so negative 4 plus 2 will be negative 2, and less than x at less than 6. So we haven't finished it yet. We need to consider the endpoint of a series. So what happened if the x equal to 2? And what happened if the x equal to 6? So we don't know if they converge or diverges when x equal to 2 or x equal to 6. So in this case, we need to consider the endpoint of the series. Where, I'm sorry?
For a second, can you go back?
Yeah. For this part, it just I mean, you need to make sure that this less than 1, because the conversions, making the ratio test for the conversion or for the root test is basically have to less than 1 for that part. And so this is the thing that we can solve. But remember, this question does not involve any factorials. So I don't really have to. I don't really have to use the ratio test. I think I can use the root test in order to solve for this question. That's gonna be a lot easier. I feel like using the root test is a lot easier than using the ratio test. So I don't have to rewrite the term with all of that. And so this is the thing that we're gonna. This is multiplications, right? Multiplied by the reciprocal. Remember, when you divide it by AK, you just need to divide it by this term, but you need to flip them. You need to multiply by the reciprocal of that, which is 4 to the k over x minus 2 to the k. So you can save time by doing so. And so on and so forth. And then we need to consider the series at x equal to negative 2 and x equal to 6. Why do we have to consider the point? Because we don't know if when x equal to 2, the endpoint, if the series converges, or x equal to 6, the series converges. So I need to rewrite a series that we have right there. So with respect to with respect to what? Let me just double check that real quick. With respect to x minus 2 to the k over 4 to the k. And what we have here will be negative 1 to the k, and x minus 2 to the k over 4 to the k. Right. Okay, so I plug in x equal to 2. So when x equal to 2, I'm sorry, negative 2. So the whole series that we have is 0, infinity, from negative 1 to the k. I plug in negative 2. I plug x equal to negative 2. So we're going to get negative 2 minus 2, which is negative 4 over 4 to the k. Right? And the whole series become, so again, negative 4. So we just do it first slowly. If we know the fact that the entire answer is 1, that's simple, but we need to make sure that we understand what we have right there. So that'll be negative 4 to the k and over 4 to the k. So the entire term that we have, we know the fact that, so negative 1 to the k times negative 4 to the k, the whole series going to divergence, right? So because the whole terms, I can combine them, so that'll be 0 and infinity. And so negative 1 to the k times negative 4 to the k, so negative 1 to the k times negative 4 to the k. So we can combine the power, so that becomes negative 1 times negative 4, so that'll be 4 to the k. So the entire thing turns out to be 1. So we divide by 4 to the k is 1. So remember, when you add up the 1 together, 1, 1, 1, 1, of course that's going to be the divergence series, divergence. Okay. And so when x equals to 6, so what's going on for the series that we have here will be from 0 to infinity. And so from negative 1 to the k, and now we're going to have to rewrite 6 minus 2 to the k over 4 to the k. And apparently that we can rewrite the series. So 6 minus 2 is 4. Right? 6 minus 2 is 4. So 4 to the k over 4 to the k is 1. So the whole term will be negative 1 to the k times 1, right? Times 1, which is that. So what we have for that part, this is also the alternating series, but this is not the increasing series, right? So the limit is not equal to 0. This is not a increasing series. It's keep 1, 1, 1, 1. So we can have 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. And then you sort of feel like, well, okay, so the answer should be 1. But the fact is, it doesn't satisfy the convert. So this is a weird part for that part. So even if you might end up getting a certain thing like 1 plus, so 1 minus 1 plus 1 minus 1 plus 1 minus 1. You sort of feel like it's convergence. Actually, no. Right? And it's divergent. So 1 minus 1 plus 1 minus 1. How can you think of this series? Right? It should be convergence equal to 1 for sure, but this is actually a divergent series. Divergent series. Okay, so it doesn't satisfy the conversion rule that we have right there. So it's divergent by the test, by divergent test. So the series, the interval for the series. So we can account these 2 points. So the interval for the series, basically have to be from negative 2 to 6, right? So the interval, I can rewrite this in terms of negative 2 to 6. I mean the radius, you can write the radius basically negative 2 less than x less than 6. So yeah, we can't include the equal sign for that part. So basically the sixth thing that we have. So now we're gonna go to another example and see how it's going to help us for this part. Okay, and then we're gonna come back to and you check on a certain problem. You can check if this guy are going to be convergent or divergent. So some of you might be asking me if we can't use the root test for this part. So the answer is yes. So how can we use the root test? So this is a different approach. We can use root test for this part because why not? So let me just tell you that part. So we can literally rewrite the series with respect to -1 to the k, and I can also convert that to the entire thing. So that would be x minus 2. I can combine the k together over 4 to the k. Okay. Why can we do so? Because they have the same powers, right? So so I can combine the terms. So I can combine the fractions. So this is literally the k power, right? So the power for the entire term. So this is the power for entire terms. So I feel like using the root test is really very straightforward strategy. And so the root test is meaning that the root test is literally what is the root test? So let me to remind you that would be the limits of k go to infinity. And then we take the k root for a to the k, right? So it doesn't involve the next or the previous term for that part. We just literally have to take the power for that and see what it is. So that would be the limit of k go to infinity. And then the k root of ak. So what is the ak? The k root of ak. So that would be this guy, x minus 2 over 4, and then raised to the k power. So the k root and k power to cancel it out, and that's become x minus 2 over 4. In other words, the root test just literally to get rid of the k power. Just take the limit of the x minus 2 over 4 as symbol as we have right there. So we just take the limits of x minus 2 over 4 and then making sure that we have the absolute value. So I forgot to do that for that example. So making sure that we have the absolute value. So let me just erase this and change that to the absolute values. Okay, change that to the absolute value. So so now the term that turns out to be a so I want the limit less than 1, right? So that's basically the same thing as we have earlier, which is the thing that x minus 2 over 4 less than 1. So they both use the same answers, but taking the ratio test on that example is, I would say, a little more complicated because we need to simplify x minus 2, k plus 1, and then x minus 2k. We're going to get x minus 2 on the top, and the bottom will be 4k over k, 4k plus 1. So we're going to get 4 at the bottom. So using the root test is actually faster on that example when we can rewrite a term as a whole. So now we're going to see some of the assignments. So I think I give the problem of the exam review. So let me just go to the textbook and see how it's go. And let me just go to the problem real quick, and then so that'll be the question chapter 11. And let me just check them and see what it is. So that should be 11.2. I combine 11.3 and 11.2 together. So let me just go to this. Oops. All right, so for example, if I want to find a power series for certain terms like it's question number 31, just any question that you feel easier, you can just do that as well. And I mean, we can do that. This as simple as we have right there. So, all right. So let's take a look at question number 31 for this part. Is question number 31 that we have was we want to find out the power of series of that part. So 31 that we have is x to the 2k plus 1 over 3k plus minus 1. X to the you can take any example, so I don't know. You can find me any problem from the book, and then let's do it. So x to the 2k plus 1 over 3 to the k minus 1. So this is where the k go from 0 to infinity, right? So we need to take the power series for that part. So the power series that we're going to have here would be so we can actually if we can write that power as a whole, that would be very straightforward. If we cannot do so, then we're gonna take the ratio test, right? The ratio test that we're going to deal with. So so this is what the question asking, find the radius of the conversions. Yeah. So the ratio test that we're going to have is we're going to take the R will be the limits from k go to infinity, and this is 8 to the k plus 1 over 8 to the k. Okay, and then we take the limit for that part. Given that, so we need to rewrite the k plus 1, so with respect to the limits of k go to infinity. And so 8k plus 1, so that'll be, you increase the power by 1, so that'll be x to the 2k plus 1. So remember, you have to replace k by k plus 1 and plus 1 over, so 3 to the k plus 1 minus 1 is 3 to the k, and then we multiply by the same terms. So I'm sorry, we divide it by 8 to the k, so meaning that we multiply by the reciprocal, so that would be 3 to the k minus 1 over x to the 2k plus 1. So in order to save space, so this guy that we know that this is 2k plus 3, right? And x to the 2k plus 3, and the bottom is, so this is 3k minus 1 over 3k. So we know the fact that the entire terms will be the limits of k go to infinity. And we're going to have x squared over 3. Right, so 2k plus 3 over 2k plus 1, so we're going to get x squared over, so 3k minus 1 over 3k, that'll be 3. And we need to make sure that the ratio test, the r less than 1, so that the series converges. So meaning that we have to deal with the term, which is, so we have to deal with the term, so x squared over 3 less than 1, meaning that we need to multiply both sides by 3. So we're going to get x squared factorial less than 3. Okay, and then meaning that, so x squared less than 3, meaning that we can also expand it, which is negative 3 less than x squared less than 3. But we know the fact that x squared always positive, so that's replace this by 0. Okay, as simple as we have right there. Okay, so when x squared less than 3, meaning that x should be bounded between negative radical 3 and positive radical 3. And positive 3, radical 3, I'm sorry. Correct? So remember that we just deal with a very straightforward okay, so we can have that part getting done. So, and so after that, we're gonna consider consider the inequality, consider the endpoint for the series. So the endpoint for x equal to negative radical 3 and x equal to positive radical 3. So negative radical 3 and positive radical 3. So when we consider the endpoint, so when x equal to negative radical 3, I can rewrite the entire series. I'm going to plug in negative radical 3 to the power 2x 2k plus 1 and over 3 to the k minus 1. Remember, the series for the endpoint should be very, very beautiful. Should be very easy, right? It can't be really complicated terms on that example. So what we can write about this guy is we have a negative 1, right? So I'm going to bring out the negative terms, negative size right there. Okay, to the k. And then go from 0 to infinity. Okay, and after that, we need to multiply by radical 3 raised to the 2k plus 1, right? So that would be 3k. So the entire thing that we're going to deal with was, so we pull out the negative side. So we remember that we have radical 3 of the 2k. So the answer will be 3 to the k, right? So make sure that we know what this is. And if you have 2k plus 1, so 3 to the k is times radical 3. But this radical term is not its floating point. So this radical term doesn't affect the convergence or divergence series. Just a constant, just multiply by 1.732 or whatever it is, right? So the most important thing that we take out a term that go with the k powers times radical 3 over 3k minus 1. So now when we consider the series, that is the thing that we going to deal with, and we cancel it out with 3k and 3k minus 1. So we're gonna have 3 on the top, correct? So the entire things that we're going to have will be from 0 to infinity and negative 1 to the k times, so 3k over 3k minus 1. So the entire thing that turns out to be 3 times radical 3. So again, when you have a same term like that, this has to be divergence, right? By divergent test. Okay, divergence. Divergent series. And similarly, when x equal to positive k, when x equal to positive radical 3. So when we have the positive terms, so the entire thing, I'm not going to do so, so I just rewrite the answers. So pretty much the same thing without the negative terms, so that becomes 0 to infinity. 3 radical 3, so this also diverges. So that will be the final answer for this part. 3 to the radical 3, so this term divergence. Yeah. So what we can tell is that the interval of the convergence, so the interval of convergence, the radius between -3 to +3, but the interval of the convergence should be the same thing. So that would become -radical 3 and +radical 3. That's symbol we have right there. So okay, and then now we're gonna move to the next part of it. So where we go to have a third problem. Just do one more problem. Just so let's say we do question number question number 19 or whatever one. So I don't mind doing any problems with that part, to be completely honest. Yeah, but I'm trying to avoid divergent series. So this series going to diverges for sure. And so let's do question number 26. So and then I will call it a for that part. So question number 26 on the list. I mean, we gotta move to the next part of it. I'm gonna come back to figure out the divergence series of this part and the radius of the convergence or arctangs for this guy. So I claim this is convergence for all x. So we're gonna deal with that. Right? I'm sorry, arctang is actually conversion for x less than 1. So we're gonna deal with that. So question number 26 that we had was the summations from 0 to infinity. And we deal with that from 3k plus 2, 3x plus 2, and raised to the k power over k. Right. So what is the divergence? So let me check that. Okay, so that is started from 1. I'm sorry with that. So started from 1. It's not from 0 because 0 we make the series undefined. And now we need to work on this example, and then we definitely going to take the ratio test. So the ratio test was that we developed for the R will be the limits going from k to infinity, right? Go to infinity of ak plus 1 over ak. And then we're gonna have to deal with that. And then we're gonna take the limits of k go to infinity, and then we're gonna have like so 3x plus 2. So k plus 1 is right, raised to the k plus 1 over k plus 1 in this case, and multiplied by the reciprocal of the term that we have. So that'd be k over 3x plus 2k. And after that, we're going to cancel it out. And then we're going to have 3x plus 2. Okay, so the limit will be, so k and k, so that'd be 3x plus 2 times the limits of k go to infinity of k over k plus 1. Right, so but this guy basically wants right? The only thing that make r less than 1 is that the x have to be less than 1, or at 3x plus 2. So 3x plus 2, absolute value should be less than 1. So meaning that we're going to expand the series, so we're going to subtract, put down -1s of 3x plus 2, about it from -1 and 1. And then I subtract 2 both sides. I subtract 2 both sides. I'm sorry, 3 sides. I'm going to get, subtract 2, 3 sides in this case. I'm going to get, so -1 minus 2 is -3, less than 3x, less than, so -1 minus 2 is -1. And I divide both sides by 3. I divide both sides by 3. So I got the radius of the convergence. So the radius of the convergence is from -1 less than x and less than -1/3. Correct? And and after that, we just need to consider the endpoint. Consider the endpoint for x equal to -1 and x equal to -1/3. Okay, so all we need to do, so when x equal to -1, so when x equal to -1, so we test out the series. Should be very, very straightforward. It should be very beautiful. From 1 to infinity, right? So I plug in x equal to -1, so we're going to get -3. And so -1 times 3 is -3 plus 2 over k is right there. So -1, -3 plus 2. So we know the fact that this is -1 to the k. This is the this is the alternating harmonic series. So we know the fact that this is converges, right? So why this is convergent? Because 1 over k diverges with -1 to the k over k is harmonic, alternating harmonic series. So this is convergence. Because by harmonic series test, by alternating series test, we need to test that part, right? So how can we test that? We need to make sure that 1 over k is always decreasing, and the limits for that part go to 0. Limits of 1 over k go to 0. So most of you actually make mistakes when we write them down the harmonic series. So we need to make sure that the term decreasing and the limits equal to 0. Only 1 or 2 people actually got it done correctly on the quiz. So when x equal to -1/3, -1/3. So we're gonna have a series from 1 to infinity. So I'm gonna replace x by -1/3. I solve for that. So 3 times -1/3 plus 2 raised to the k power over k. So we know the fact that 3 over 3, so that would be -1. So -1 plus 2, so that would be +1. So +1 to the k is 1 over k. So we know this is diverges, right? So 1 over k is diverges. Okay, diverges. 1 over k squared because p equal to 1 for that part. So so pretty much it. So the interval series, so we need to include the equal sign for -1s, right? So the radius of the convergence that we need to have was will be -1. So we have the equal sign. This is convergence, and we also write down the interval convergence. of the convergence will be between, so remember when we include ones, negative ones, so I have to put the bracket. So -1 to negative 1/3. So the 1/3, the series diverges. So we have to put down a parenthesis for that. Okay. So now we're gonna test on the arctang of the question. So with the arctang, so let's say we know the series for the arctang is -1 to the k to the 2k over 2k plus 1. Okay, so the arctangs of the series, let me just do that real quick. The arctangs. So let me just arctang of x. We can also rewrite in terms of the series of -1 to the k when my k go from 0 to infinity, and this is x to the 2k plus 1 over our 2k plus 1. Right? So I want to find the radius of the convergence for that part. Even if you look at that, it's literally less than 1. So I'm going to show you what it is. And so for that part, we need to take the ratio test. So that would be the limit of k go to infinity. So we're going to take the ak plus 1 over ak. And then in this case that we're going to take the limit of k go to infinity. Right? So ak plus 1 is x to the 2k plus 3. So I might just simplify it. And it's 2k, so 2k plus 1 plus 1, so that'd be 2k plus 3. We have a parenthesis for this, and so that'll be 2k plus 3. And we multiply by the reciprocal of x to the 2k plus 1 over 2k plus 1, so that'll be 2k plus 1 on top. And over x to the 2k plus 1. Okay, and then so when we take the limit for this part, so x to the, so this guy going to be x squared, right? So I'm going to put that x squared on top of this. So this guy will be x squared multiplied by the limits of k go to infinity, and we're going to get 2k plus 1 over 2k plus 3. So we know the fact that this, so when k go to infinity, so they have the same ratio, and then this is going to be 1. Right? So we want to make sure that x squared less than 1, meaning that we solve for that less than 1 because we need to make sure that all are less than 1. And so meaning that x squared less than 1, right? Because the whole term of the limit's actually less than 1 for sure. So x squared less than 1. So meaning that x squared less than 1 greater than 0. And so that x basically bounded between 1 and -1. Okay, so and after that we can deal with you can consider the endpoint. Consider the endpoint for the arctangs when x equal to -1 and x equal to 1. Okay, so for that part, so when x equal to -1, what's going on for that was when x equal to -1, so the entire series that go from 0 to infinity. Literally, so I plug in x equal to -1s, right? So that'd be -1 to the k and times x to the, so -1s raised to the 2k plus 1 over 2k plus 1. So we need to analyze that. So -1 to the k times -1 to the 2k times -1s, right? So for that part, we need to remember this guy is -1s, +1. So remember that part. So we have right. So think of it. It's for that part. So this is -1 to the 3k. So -1 to the 3k times -1, which is +1 for that part. I'm sorry, stupid -1. I apologize. So right, and so -1 to the k times -1 to the 2k. So we're gonna have -1 to the 3k. We want to make sure that it is positive and negative. It's really important. If we determine the wrong terms, then we're gonna get it wrong. So for that example that we can definitely gonna check that the whole series here, so that'll be -1 to the 3k plus 1, right? 3k plus 1. So with k equal to 0, so that one is 0. That's what is negative. With k equal to 2, that's what is negative. When k equal to 3, that's one is positive. 4, that's what -5, positive. So we have like a negative sign in the front, right? So I simplify all of that. So that becomes -1 to the k over 2k plus 1. So this guy is definitely gonna be the same as, pretty much the same, but it's the ratio of 1/2. So that would be the same as -1s to the k over k, right? Using the limit of comparison test, we need to find a limit for that part. It's 1/2, right? So this is convergence. Yeah. Okay, convergence. Similarly, that we have x equal to +1, that we're gonna have a certain thing from 0 to infinity, and we have like a from -1 to the k multiplied by, so that'd be 1 to the 2k plus 1. So this one is positive, so that'd be 2k plus 1, right? So this guy is 1. So 1 raised to the power something, also 1. So the entire series can be written down as -1 to the 2k. The same thing, basically. So the top is actually harder to determine because we need to consider this. We need to combine the power for -1s, but for this guy, it's pretty straightforward. And this guy also convergence similar to that. And so the radius of the convergence that we can rewrite, the radius of convergence that we can write them down as -1 less than or equal to x and less than or equal to 1, right? So the interval that we can, a convergence that we can write from -1 to 1 to +1. Okay, so that's pretty much the thing that we need to deal with. Okay, so I feel like that's got to be a little bit the thing. And so let me just read the note if I have to do anything else for that part.
And so this is how we rewrite them, and if you can read the note out, that would be great. And so this is how we deal with diverges. I think I'm making mistakes right there, so that should be -1 -1 to the so that should be 3k plus 1, so that is converges as well. So I make a mistake for that part for some reason. And again, that we can consider a certain power series. I can also rewrite the power series given by the thing that we have. So let's say finally that this is a thing. So again, after this we're done for the lectures. So 1/1 minus x. So 1/x, 1/1 minus x. I can also rewrite this term as the sum of x to the n, x to the k from 0 to k. So wait, let's say I take x to the 5th, right? And then 1 minus x. So I can just read, so this is basically x to the 5th times 1/1 minus x. And this guy can also rewrite as a power series of that part. So this guy will be the summations of x to the k and from 0 to k. And then I can combine them, which is x to the 5, x to the k plus 5. As symbol set from 0 to infinity. Okay, so from 0 to infinity. So what happened when we have like a x to the 5th, 1/1 minus 2x. And I can also rewrite this as, so I replace x by 2x, basically the thing that we have right here. I think I went over this part, so that'll be from 0 to infinity. The radius of the convergence for all of these cases still be 1 minus x, because it's basically coming from a series. We just multiply by a certain constant and dividing, so it's not going to be a big deal. So that'll be from 0 to infinity, 2 to the k times x to the k. Remember, the whole point, the radius of convergence will be from -1 to +1. So for both cases, for all of these cases, we need to know what is the value of x that's going to make the series converges. So they have to be the same. They originally coming from 1/1 minus x from the geometric series perspective. So that would be the thing that we have right there. And that's pretty much identify the series. Literally, that this is the thing that we need to rewrite them, and sometimes we replace this. So it's not going to be a big deal. So generally, this is x to the k. Pretty much I replace 1 minus 2x by x to the k. So this is basically e to the 1 minus 2x as simple as that. But all right. So generally, this is what we have done. And if we have any problem emerge Wednesday. So again, there will be a quiz on Wednesday. So that'll be the last quiz. And after that, we had a final exam on May 13, and that's pretty much it. But the quiz is gonna be focusing on the Taylor series. I'm gonna write down the Taylor series at x equal to pi, or x equal to 0, which is a special term for the Maclaurin series. So this is where we need to use the derivative for the Taylor's one, the Taylor forms, and you can write them down like that. However, that we can also, we need to know how to determine the convergence or divergence, the radius of convergence or divergence as well. So that will be the last quiz on Wednesday. So that will be on May 6th. And after that, we no longer have classes, but I will be here on 11 for those of you who come and ask me the questions. And other than that, that's pretty much it. So this is the entire course for chapter 11, and that was also the end of Calc 2 for the lectures. Okay. So generally, this is a thing that we have to do. And again, when we do the final exam on May 13th, then we're not going to see each other again. So that's really the last day of class, and that's pretty much it. So again, that I will basically going to see each other again on May 6th. I'm going to point out the topic and what we should know about this, what form that we need to use, and then we're going to work through some of the practice problem. So this is a thing that we're going to have for the study guide solutions. So we're going to go to the final exam solutions. And of course, there will be a video posted. So those of you who actually have questions, please ask. And so we're going to work through every single question for this part. Okay, so I will see you guys back on Wednesday. Remember, there will be quiz number 7, focusing on the chapter 11. Okay, stay safe, and I'll see you guys next time.
Thank you.
Wait, Professor. Sorry. Are we gonna get? You gonna have like our quizzes graded?
I think I graded the quizzes, but.
Oh, really?
Yeah.
Oh, okay. I guess it just didn't show. All right, thank you.
You're gonna check the grade on a submitted grade, whatever. So. I think,
okay.
Yeah.
Okay.
I'll post solution on that. Yeah. So.
Okay. Thank you.
Well, so have a great night, everybody.
Professor?
Yeah.
Okay, so I'm a little confused. What exact, for the question, what do we, box in? What is the question specifically asking?
So the question specifically asking, let's say we want to find the radius of convergence. So in this case, that we need to use the ratio test or the root test. The root test doesn't work in this case. So meaning that we going to figure out the range that the range value of x that's going to make the series converges. So let's say we have a few questions like that, for example. Let's say, can I use the size of x to figure out the cosize of x? So those are not asking us to find the radius of convergence. We just literally need to find the explicit formula that represent the series. So let's say we can find the cosize of x using Taylor series. If the question asks us to use the Taylor series, then we have to write out the formulas f prime at the center equals 0, for example, f of 0 plus f prime 0 times x plus f second prime 0 times x squared, and so on and so forth, right? And so if the question only asks us, for example, can I solve for, can I write down a cosize of x the power series using the size of x the power series? So the size of x using the size of x, that should be this guy, for example. So we're going to take derivative for that part, and then we solve for this, and then we're going to get the cosize of x, theta, cosize of x power series using the size of x power series. See what I'm saying? So when the question asks us to do so, then we have to do it that way. If the question asks us to write down so for example, there was a final exam reviews, for example, that we have the just this example. So we can also use the power series. So the power series for e to the x, which is x to the k over k factorial, and times k. We can also do that, but and then we're gonna get the summations of x to the k plus 1 over k factorial, for example. So this is where we're going to have to deal with, instead of we writing down a Taylor series. So when I use the Taylor series for the final exam study guide for x times e to the x, for example, so I got the same thing. So I take this first derivative, second derivative, third derivative, and I do so, I'm going to get x to the k plus 1 over k factorial. But in this case, I can literally just apply e to the x power series and solve for that. And I'm going to get the same thing, but it depends on what the question is asking to do. In this case, if we use the e to the x, the question has to give us e to the x, which is pretty much like the last question. So for example, the question gives us the Taylor series for e to the x will be x to the k over k factorial. So we want to rewrite what is the x times e to 2x. So I replace x by 2x. So I'm going to get 2x to the k power. And then I multiply by x so, and I'm going to get this.
So that's what we box in?
Yeah, this is what we need to do. So some people might want to use a Taylor series to solve for that, but it depends on the question. If the question asks it to use the Taylor series, then we have to deal with the x prime, x second prime, third prime, fourth prime to solve all the polynomial functions. If the question gives us like use a certain fact to solve for the Taylor series, for example, the cosine of x, then we're not going to use the Taylor series because the Taylor series is basically complicated. I have to do the first derivative, second derivative, third derivative. I mean, we can skip all of this work if the questions doesn't give it that. In fact, most of us actually use this strategy to check for the Taylor series term. So for example, that when we take the second derivative, for example, we take that example, the third derivative, you might make mistakes on it. So we get a certain term that is not correct. So we can check if my functions actually equal to this one. So if we got the same thing, that is correct.
Okay, so for the two examples that we did from the textbook.
Yeah, two examples we did from the textbook basically asking us to find the radius of the convergence. So the radius of the convergence is basically asking us to figure out what is the range of the x that we're going to make the series converges. So for example, when it comes to the final exam, that we can see that the question state very clear that we need to find the radius and interval of the convergence of a certain terms, and using the ratio test, which is R instead of L. I'm not sure why I put down the L. For some reason, I don't know. Should be R, and then we can also deal with that. And generally, this is the thing that we need to have to do. Okay, for chapter 11.
So for that question, we would have to box in the -3 have
less than
x. That's what we box in.
Yeah, but we need to consider the inequality when x equal to -3/2 and +3/2 to write down the interval of the convergence. Correct.
Got it. Okay.
All right. So depending on the question, if the question, remember, there will be 3 types of question for chapter 11. The first, that we need to use the Taylor series that we covered last class. The second, I might give you any specific functions. Let's say I give you 1/1 minus x, and then can you find me the Taylor series for x to the 5th over 1 minus x? So this will be another questions. Or can you find me 1/1 minus 2x? That will be another questions. Or I may ask you to find, hey, what is the value of x that will make the series convergence? So this is what we call the radius or the interval of the convergence. Okay, so I hope you guys going to get this through. If you don't get it through, we're gonna see each other again on May 6th. And please ask questions for the final exam review. I might go over this and then the earlier part, and then we're gonna spend time on May 11th to go over more things. I mean, we officially do not have class on May 11th, but I give you guys the additional review for the final exam before we have the final on May 13th. Again, that the final exam should be 24 hours, but you need to submit it before that when you start it. We have 5 hours to finish. You can start anytime between 1 hour for that. I'm sorry, between 6 p.m. to 6 p.m. on the next day, which is Thursday. All right, so I hope that you guys going to stay well, stay safe, and I'll see you guys next time on Wednesday. Take care.
Thank you.
Yes.